Hello everyone. We've got light to talk about, and it's not a light matter. Before we get to light, this is a fairly advanced thing. If you don't want to pay attention to this because you're never going to do differential equations or higher level physics or engineering, that's okay. But I do want to explain where some stuff comes from that you've seen in other places. And so, with that in mind, this is the state of electricity and magnetism up to, well, we haven't gotten into induction yet, so we'll get there in a second. So, first part is Gauss's law. We talked about Gauss's law a bit. I'm not too worried about that. But you've seen Gauss's law before. It's this ugly integral of the electric field going through some area is going to be the charge enclosed over epsilon naught. The second one is a definition of potential. Is saying that this product of the electric field and some direction vector is going to give you your change in potential. So this is the change in potential between points. Now, if we close this, then this bit should be 0. Right, because we have some thing that's, we have some point that's at some potential, and we're going all the way around, right? We're going from this point back to this point, so delta V is 0. However, we talked about Faraday's law. We talked about Lenz's law, and those two things are going to tell us that we could have some potential difference, in this case the electromotive force, that's due to the changing magnetic field in here. And so we can end up writing this as, in the closed form, minus change in the flux, the magnetic flux over time, times maybe a number of turns somewhere. Since this is going to be one turn that we're going to look at, we'll drop that. All right. So that's what we have for our definition of potential. Is if we have a closed loop like we do in Gauss's law or in the other laws here, then we only have a potential if we have a changing field. I swear this is leading to light. This third equation is Gauss's law for magnetism. And what it really says is there are no magnetic charges. All the things that you've seen that generate magnetism look like current loops. They don't look like a single charge somewhere that's emitting a magnetic field, like the charges emit electric field. All right. Now, this thing down here is Ampere's law. You've seen that a little bit. And the idea is that if we draw some loop around a bit of circuit, then we have some enclosed current. And so that leads us to this picture on the right. We have a voltage, and that voltage is being fed into a capacitor. So we have some current flowing up here. And that'll be our enclosed current. And going through here, if we take this loop, this is going to be our DL down here, we can calculate the magnetic field based on this. Right? And this gives us B is mu naught I over 2 pi r. Because B is going to be constant on that loop, and I is going to be constant, so everything comes out of the integral except the circumference of the loop. So we'll put in R. Right. So what if I draw that loop in the capacitor? Right? What's happening is as this charge flows, and you have the corresponding enclosed current there, current can't flow across this. That's by definition. there's an insulator in there that is storing charge. There's positive charge building up on the top plate and negative charge building up on the bottom plate. So if I put a loop here, the same as that loop, there should not be a magnetic field there. However, if we build this circuit, there is. And that implies that this thing is not completely correct. And you can, go and look at this a little bit in your other notes. But what I'm going to suggest is that we tack on something that looks like this, that references the flux changing through this. Because what's happening is this doesn't happen all at once. We put some charge on, and then it takes more energy to put more charge on. And so the current, the actual current, looks like that. Looks like that decay function. That's what we saw when we talked about capacitors, is the current that's available to charge up the capacitor drops over time. So there should be some function that we can put in here and talk about the potential over time, which is doing that number. And what we end up putting in here is a term that looks like, and I'm going to check my notes just to make sure I'm doing this correctly. There's a plus sign here. We're going to have this to make their units right, and then I'll make this to make our units right. It'll look like that. This term, this bit, which I'm going to put in dotted form, is termed a displacement current. So that sets these equations correct. And everything's coming in on the video. That's good. This might be a long video, but that's okay. So this sets everything. These equations look pretty to a physicist. They look like they're in the right orientation. You got symmetry. You've got an electric field equation and a magnetic field equation in area. And you got one of each in length. And then you got two in electric fields, two in magnetic fields. You have one involves a changing magnetic flux and one involves a changing electric flux. You have one that involves an enclosed charge and you have another that involves an enclosed charge. And you do have, technically, right, you could have a non-closed loop. And so you could have something here which essentially would, make some sense like a current. And you'd have something here that makes sense like a current. You could also, in this thing, have a magnetic current, but because there's no magnetic charge, it's fine. All right, so this is a nice set of equations. This is the integral form of Maxwell's equations. Now, I'm going to erase all this over here that you've seen, but I'm going to leave this up because we're going to talk some derivatives here for a second. So, we've had, in the past, we've had some defining derivatives going on. We had this symbol, which is defined as d over dx I hat plus d over dy j hat plus d over dz k hat. And so you can write something like grad of a function we'll call phi. This is the gradient function. And this is just d phi dx I hat plus d phi dx j hat plus, d phi dy plus d phi dz k hat. All right. So this thing looks remarkably like a vector. It has components I, j, k, and those components are what are called operators. You apply them to a function and you get something out of them. So we can continue this. If this thing looks like a vector, well, we can take dot products. And so there's our dot product. And this thing is called a divergence. And so we can write out what that is. That is d phi of x dx plus d phi y dy plus d phi z, not phi, a. And that is a number. This is a vector. And we talked about this a little bit in other realms. The divergence is, if I have a point, how much does the vector here spread out from some point? How much does it look like an electric charge? Now, we can also talk about what's called the curl, which is taking a cross product. And for reasons, this sucks. But the idea is that the I part is the AY dz minus dAz over dy plus j hat. And the way we do this is in determinants. If you've seen linear algebra, this is I, j, k, d dx, d dy, d dz, ax, ay, az. And if you can take a determinant of that, you figure out the entire cross product. The point is, it's a function that's defined, and whatever this is, it is a vector. So we can apply these things to the electric field and the magnetic field because they are both vectors. And even better, we can take these forms of the equations and turn them into derivative equations instead of integral equations. This one up here is how much does the electric field diverge? Well, it depends on the density of charge. This one here is going to be how much does the electric field curl. For curl, this is, if I have a point here, how much does the vector wrap around it? So for all of these things, you have some point, you have the diverging part, and then you have the curling part. And you can write this a couple of different times in different directions. All right, you could have it going around like that. So you can say each of these vectors has some part that diverges and some part that curls. A lot like taking the r direction and the theta direction. Right? So this part is going to be curl of E. It's going to be how much does the magnetic field change. And it's important here in the sense that what we're doing is using some deep math that says when we have an area integral like this, we can change it into the derivative of a volume integral. When we have a line integral like this, we can change it into the derivative of an area integral. And there's a few others like that. So that's why we're just jumping to these things. You've seen these before somewhere, like on a t-shirt or on some TV show. This one is the divergence of B, right? It just depends on the function. It's not depending on the field. Ends up being 0. This one is curl of B is mu naught I enclosed over volume, right? Because it's going to be a density. In this case, it's the current density, plus mu naught epsilon naught dE dt. And that is what's called Maxwell's equations. If you've not went and did popular stuff, Maxwell was the guy that sat and studied these things. He didn't have nice terminology. If you have no idea what I'm writing here, it's okay. The idea is he didn't know either. He didn't have this. He did it component by component. He's like, what is the Z component of the magnetic field going to look like? And math has given us all this terminology. But the point of it is, all these integrals and all these derivatives are equations that we can solve for the various things. And in particular, we can come up with one more set of definitions here. And at this point, I got to erase some stuff. I'm out of board. So we can define the square of this operator, which is basically taking the second derivative. And it is the divergence of a curl, the divergence of a gradient. But we can define it as d squared x, d squared of a function over dx squared plus d squared over dy squared plus d squared over dz squared. And this works fairly well, right? So the idea is we can define this thing. We can take our functions that we had before for the electric and the magnetic field, and we can go and write new functions that combine the things. Now, I'm not going to go into it here, but the point is, when we talked about in waves, we had some wave function. Y of x and t looks like some amplitude times cosine kx, which makes us it's wave number times the position, so it comes out unitless. And actually, we can write it as 2 pi over lambda x, so we have the wavelength in here, plus 2 pi f t. This is omega. So k is 2 pi over lambda, and omega is 2 pi f. And then a correction term so that we start the wave where we want to. The idea is we have a plot somewhere, and maybe we want it to start going up like that. Right? And so the correction term says essentially what is the value at x equals 0. It makes everything work out right. But this thing came from a wave equation, and the wave equation looked like d squared y over dx squared is, I think, 1 over v squared d squared y over dt squared, or something like that. We got, this is going to be in units of y, so when we take two derivatives, we should get 2 divisions by It's going to be kind of, let's see, we're going to have over here 2 divisions by distance, and then we're going to have, so that, I believe the units are right on that. Point of this is, we have light as an electromagnetic wave, and we'd like to talk about what is the wave equation for it. And we can do that. For light, we have the electric field as x and t. It's going to look like some maximum electric field for our amplitude times cosine kx minus omega t plus phi. And then we'll also substitute in b of x and t is b max cosine kx minus omega t plus. And we may have a different phase factor. Right? Those are our wave equations, and they come from some function, and this function is going to look something like this. It ends up looking like d squared e over dt squared is 1 over mu naught epsilon naught. No, let me do it right. There's x squared here. There's mu naught epsilon naught d squared e over dt squared. I wonder if I have that right. Yes, I do. Hot damn. And then you'd also have d squared b over dx squared is mu naught epsilon naught d squared b over dt squared. This thing in here, the mu naught epsilon naught, that will end up being the speed of light squared. Or 1 over the speed of light squared. The big deal is what we have up here is, let me get a color that will show up real good. We have V is F lambda, which is these things, omega over K. But in the electric and magnetic fields, they have slightly different meaning. Is that they're going to have something to do with these mu naughts and epsilon naughts is where they come from. But this should equal C is 299,792,458 meters per second. But that is 1 over square root mu naught epsilon naught. And if you have a calculator out, you should go and multiply those out and show that indeed it comes really close to the correct number. Of course, we round, so you're not going to get it perfect, but that's what it is. Now, I've spent 24 minutes here ranting about something that no one needs to know today. So, understand that if you have questions later on about where does this stuff come from, where I'm making up a bunch of numbers, you need to see this video. Otherwise, that's where we are. So I'm going to pause this and do another video.